excellent reports. So let's welcome Professor Song.
Thank you, Professor Song. I think we are running a little bit of time. And actually, to be frank, out of the speakers this afternoon, I'm the one least close to information theory. So I look at all my research, I tried very hard to find some topics which is related. Actually, my background is wireless communication. So I focus on wireless communication and machine learning. It's very nice to see Professor Bai as expert in information theory, and also Professor Li, all the interesting talks. Okay, let's start. So my talk will be a little bit related to information theory, but I'm a system guy, so it's about MIMO system. So we want to actually understand what is the fundamental limits of a MIMO system. Okay, let's start. So there will be three parts. First, a brief introduction, then there will be three works related, and then I will draw the conclusion. Okay, so we all know wireless communication has actually evolved several generations. At the beginning, we are using mobile phones to connect people by voice and message, and later we began to connect people by applications. And nowadays, people believe moving forward, wireless network is no longer just a network to transmit information. It will be a platform which connects data, computing power, and algorithms. When you put those three together, actually you get intelligence. That's AI, right? AI only has three components: data, computing power, and algorithms. So wireless network is supposed to connect all the AI services in the future. And so moving forward to 2030, this IMT 2030, basically 6G. You can notice that there are two additional new capabilities. One is the sensing empowered, the other one is the AI empowered. So the first one is what we call integrated sensing and communication. The second one is how to integrate AI with wireless communication. I guess that's what Bob's company is now focused on. However, on the other hand, we still focus on all the conventional performance metrics. Like in 5G, we have the three pillars: URL, CEM, all those things, right? We care about connectivity, latency, reliability, throughput. So the question now is, moving from 5G to 6G, we still want to further push the performance. Then how can we do it? Looking back, there are actually two fundamental ways we have been trying very hard to improve the performance of wireless network. The first one is we want more spectrum. So if you look at how the system evolved from 2G, 3G, 4G, 5G to 6G, we are basically pushing higher frequency, right? So we want more frequency so that we have free resources to use it. So this is the one direction. We want more spectrum. On the other side, we want to improve the spectrum efficiency. Given the amount of spectrum, we want to use it more efficiently. And there are two, at least, very effective ways. The first one is to do cell densification. So we make the mobile cell smaller. So we increase the frequency reuse factor. That's what we have been doing from first generation until today. Now, if you go to Mong Kok in Hong Kong, I think the cell will be very small compared to the previous system. Now, another one also proved very effective is actually what we call MIMO, multiple input, multiple output system. So by equipping the transmitter and the receiver with multiple antennas, we can actually achieve two very important gains. We call them multiplexing gain and diversity gain. Multiplexing gain basically means you can create multiple parallel data streams between the group of transmit antennas and the group of receive antennas. Second one, the diversity gain basically can help us to improve the reliability of wireless communication system. So basically, you get a smaller bit error rate. That's the two fundamental gains. Because this has been proved very effective, and people have been pushing this on two directions. On one direction, we are making the antenna array to be larger and larger. So we go from MIMO to massive MIMO to extra large MIMO. People are talking about making all the walls of a building to covered by antennas. This is one direction. We want to make the antenna array larger. On the other hand, we are trying to reduce the spacing between the antenna elements. So basically, for all the mobile antennas, MIMO antennas, currently the space between two antenna elements is basically at least lambda over 2. half of the wavelength because people believe that's already the limit, right? However, there are research which is trying to reduce the distance between the antenna elements. So you can go from a discrete aperture to a continuous one. We haven't been able to prove this will actually give us a lot of gain, but the hope, or basically what we are trying to achieve, is by doing this, we will be able to directly manipulate the propagation of electromagnetic wave. So think about this. In the previous generation, when we do wireless communication, even physical layer guys like me, we don't really care about the transmission of the microwaves, right? We just do the baseband processing. We assume everything is done by the antenna guys. But now what we are trying to do is we make the aperture continuous, and this will directly affect all the conclusions about, people are saying this is called AICIT, electromagnetic information theory. They are saying that hopefully this will break channels. I'm not sure. Okay, by far, I haven't seen any hardware which works very well, but this is actually one of the direction we are going. So today, what I want to talk about is how to evaluate the fundamental limits of all those innovative MIMO systems. So there are some issues when we work towards large-scale MIMO system. First one, channel modeling. This will be very difficult because we are changing the hardware. We are making the antennas arrays larger. We are reducing the antenna spacing. So all the channel models we used before may no longer be valid. Second one, performance analysis. So we want to know what is the fundamental limits. When you change the antennas, when you change the channel, what will be the highest data rate you can achieve? So that's what we call fundamental limits. I'm basically going to focus on that. And then you have system design side. You have a lot of issues, like if you increase the size of antenna, how do you do channel estimation? Okay, there's a lot of issues because you need to estimate more variables, right? So you will need a large amount of palettes. How do you do that? Also, how do you develop hardware? I know like Huawei is putting a lot of efforts in developing new antennas. It's very difficult to make them massive. There's a lot of things going on. I'm a system guy. I will focus on the performance analysis part. Okay, I'm not sure about the audience, so I will try to give a brief introduction what we mean by fundamental limits. So we all know if we have a communication system, Shannon tells us there's a term called capacity. You cannot achieve a data rate above that. So what happens is for a single input, single output system, so you have a Gaussian channel. So the received signal will be the summation between the transmitted signal and the AWGN, additive white Gaussian noise. For this case, we have a formula. So the capacity is proportional to the bandwidth, but that's also related to the power and of the signal and the power of the noise. Now, what happens in wireless communication is the channel is no longer a fixed value because the base station, not base station, the mobile phone is moving. So the channel is changing. You have a variation. If you measure the channel again, you have a variation. And then you no longer have this expression. You will have something called instantaneous mutual information, which is a function of the channel gain, H here. So H, actually the absolute value H, the variation is showing in that figure. Now, for this case, when we talk about the fundamental limits of wireless communication, we don't look at instantaneous mutual information because it doesn't make any sense. There are two terms or two performance metrics. First one is what we call ergodic mutual information. So we take the expectation of the instantaneous mutual information over the channel, over the distribution. The second one is called outage. So we call it reliability because it tells us what is the chance that your data rate is less than the threshold. So if you put a threshold there, it basically tells you what is the chance the channel condition is worse than your desired performance. Actually, ergodic mutual information corresponds to throughput, the data rate, and the outage actually tells you how reliable your communication link is. So those are the two fundamental limits we look at. Now the issue is not, this is widely studied. The issue is for MIMO system, the expression of the instantaneous mutual information or Gaussian mutual information and outage will be no longer a function of a scalar h. It will be a function of some random matrices h. So basically, h here is a matrix. So the HIG, the IG's entry of this matrix represents the channel between the J transmit antenna and the S receive antenna. So that's the case. Now we need to calculate the ergodic mutual information by taking expectation over this random matrix. And we also want to know the distribution of this instantaneous mutual information to calculate outage probability. So that's what we are trying to do, especially for some novel, innovative MIMO systems. Okay, so if you look at this expression, actually you can write the instantaneous mutual information as a summation of the logarithm, and lambda here is actually represents the eigenvalue of the we call it the gram matrix, H times H H transpose. And then what happens is, for this case, we know the characteristics of the eigenvalues for this matrix will be very critical performance evaluation, and to this end, random matrix theory will play a very important role. So that's why we are relying on this tool to do a lot of performance evaluation. So I must admit, I'm not a information theory guy. We are basically using this mathematical tool to solve some communication problem. Okay, so we are not looking into developing new random matrix theory tools. We're basically using them up. Sometimes we develop a little bit, a baby step improvement. I'll show you a little bit later. Okay, so random matrix theory, actually there is a finite random matrix theory, asymptotic. Here we are using asymptotic because certain advantage of it. So what is asymptotic? It basically focuses on the limiting case when the size of the random matrix approach infinite. So for example, if you look at this example, you have a random matrix assuming this IID, independent identically distributed. And if the size is 100, if you look at the distribution of the eigenvalues, you don't see anything. However, if you increase the size to like 10,000, the distribution turns to be deterministic. That's actually the core value of random matrix theory. That's actually why we are using it, trying to solve some evaluation problem for various communication. So it has been applied to many areas: chaotic physics, signal processing, and machine learning. Actually, not nowadays. I think this is the biggest application of random matrix theory. There are lots of works going on. Okay, so why asymptotic? Why not finite? You can do finite random matrix theory. Actually, it will give you an exact analytical expression, meaning the result will be accurate. However, if you look at here, this is a work by this paper. The computation will be there will be a very high computational complexity. So normally we don't do it. And also there's another reason. This is distribution sensitive. You need to know exactly what is the distribution of the channel matrix. Now we use asymptotic because it gives you simple expression and it's easy to compute. With a simple expression, actually for a system guy like me, we are more interested into the physical insight, meaning that we want to know how the antenna size will affect the performance. We want to know how the antenna spacing will change the performance. Those are more interesting to us. I'm not a theoretical guy, so that's why we also rely on this tool. So more importantly, the ergodic mutual information and also the outage probability for wireless communication system, those two performance metrics can actually be directly evaluated by two important terms for random matrix theory: deterministic equivalence and the central limit theory. I'm going to show you some detail later. Okay, now let's look at some classical results. Actually, this has been happening in the literature for many years. So this is the first work which used finite arm MT. This work considered the correlated MIMO channels. Let me explain a little bit. So H here represents the channel matrix. X here is a IID matrix, meaning all the entries of this matrix is independent and identically distributed. They follow Gaussian distribution. And the sigma here introduce the correlation structure at the receiver side. So you have a MIMO channel at the receiver side. So this is a half way correlated case. For this work, this paper derived the ergodic mutual information, and you can see it actually is a function of the eigenvalue. But unfortunately, this calculation is very complex. So there will be some limitation to high computational complexity. Also, it will be very difficult for you to understand how changing your physical design, the MIMO antenna, will affect the performance because the very complex expression. So that's the problem. So moving forward, people began to use asymptotic RMT. So this is the work where you consider IID channel. So there is no correlation matrix. For this work, if you look at the ergodic mutual information, people was able to derive that this ergodic mutual information is somehow can be approximated by its deterministic equivalent. And if you look at this expression, there's only one parameter, and this parameter omega can be determined by a single equation. And this single equation actually, there's only one parameter, eta, and also this sigma squared, this SNR. What is eta? Eta is basically the ratio between the transmit and the receive antenna for MIMO system. So basically, through this expression, you will be able to know how change the physical design of your MIMO channel will affect the performance directly. That's why we are more interested in this design. Now, moving forward to a general correlated relay MIMO channel. So X here is still Gaussian IID. T and R represent the transmit and receive side correlation. For this case, we can get similar result. So you can look at here, this expression, this DE deterministic equivalent. There are two parameters, delta and delta tilde, and both of them can be decided by this equation. And this equation only includes the correlation matrix, R and T, and also the SNR. That's the case. So give me the correlation matrix and SNR, we'll be able to determine two parameters, and we'll be able to give you a closed form expression, although there is definitely approximation error. So that's the cost of using asymptotic measure. So yeah, the error will decrease if you increase the size of n, but there's still an error. Luckily, by far, the observation is that although asymptotic method was derived for this asymptotic region, even for system with a very small size, the approximation accuracy is actually quite high. I'm going to show you some results a little bit later. Now, people keep moving forward. They say, okay, this is for those who work on wireless communication, this is called a correlated relay. If you add a constant value, it's called Ryzen channel. A little bit of background. So what do they mean? Actually, this A part comes from what we call line of sight. So if the base station and the mobile phone, there is a direct link, there's no block between the base station and the mobile phone, you will have this what we call line of sight component. And the previous model, this one didn't consider that. This is typically what people call relay fading. And this channel comes from the reflection of the microwave from the surrounding environment. So there's no direct link, only reflections. So that's the case. That's the difference between them. Unfortunately, mathematically, you introduce this term will make the problem much more difficult, but we can still do it. So basically now the determinist equivalent is in this way. You also have two parameters which you can decide, but now there's a new term A by the line of sight component. But anyway, if you look at all the results, they're similar. You can have a closed form expression which relies on one or two parameters, and those parameters can be determined by some fixed point system of equations. Okay, so that's the benefit of using asymptotic RMT. So what I want to share with you guys today are three works we work on. They may not be very interested from an industry perspective because they are more about finding the fundamental limits of this MIMO system. So first one is the general large-scale MIMO system. So why we call it general? So we consider this model. Remember, I just mentioned A comes from the line of sight component, and the second part comes from the reflection of the environment. And in traditional wireless communication, we widely assume that X follows a Gaussian distribution. The Gaussian distribution actually comes from central limit theory because if there's a large amount of sketchers around the transmitter or the receiver, you will have a lot of copies of the transmit signal at the receiver side. And when you have a large amount of independent random variables, you sum them together, naturally they will follow Gaussian distribution. That's why really channel was so popular in wireless communication. And why we are here interested in non-Gaussian random matrix is because relay fading existed because you are using low band frequency. So for example, if you go to 2G or 3G system, the spectrum you are using, the carrier frequency you are using is low. When we move to millimeter wave, even terahertz, what happens is the path loss will be significantly more serious, meaning that the number of reflection your signal can go through will significantly be reduced. So imagine previously, I send a signal, it can hit the ceiling and hit the wall and then reach you. Now, if you work in millimeter wave or terahertz, you can hit the wall and no more. It will disappear. This means that the reason why you can have Gaussian distribution, remember central limit theorem, you need a large number of random variables, right? This no longer holds. So that means this channel matrix will no longer be Gaussian, can be some other distribution. So our work here is try to find a general way to evaluate this. What happens if X is not Gaussian? So we want to find a unified approach. However, starting from scratch is impossible. So we took a different way. We tried to do a little bit of adjustment, meaning that we are going to investigate the gap between the Gaussian channel and the non-Gaussian channel. Because the result for Gaussian channel is already known, if we can calculate the bias, we add this bias, we'll be able to get a new result. So that's what we are trying to do. So interestingly, if you look at this expression for capacity, it is actually a special form of this linear spectrum statistics. This is a very important area in random matrix theory. Basically, that means if you take f as the log function, you will go from linear spectrum statistics to capacity, right? So for this area, we actually did a little bit of contribution for random matrix theory itself, not for MIMO system. So we basically derived the bias for linear spectrum statistics for non-centered non-Gaussian. Non-Gaussian means X is not Gaussian distributed. Non-centered means you have you have the line of sight component. So this result is more from the mathematical perspective, but we apply it to evaluate MIMO system. So what we did is we can basically determine what is the bias. I'm not going to go to the details. So there are two variables here. One is the mean of the Gaussian case, and the beta f here is the bias. Now, compared to existing works, actually, we are not the first one to look into this. There have been some works. Compared to them, we basically gave a tighter bound for the error, for the approximation error. And also, this work, this HAPCHAM 12, they actually derived the bias for the variance. What we did here is we derived the bias for the mean. By putting these two together, we can give a more complete picture. Okay, so this is the simulation result. The three curves, the purple one is what we call theoretical mean bias. So basically, this is the bias for the mean of the mutual information distribution. And also we have the empirical simulation result, which is the right one. What you can see is as the size of the antenna increase, they converge. So first thing, the approximation is accurate. There's another very interesting phenomenon we found, which is the bias for the mean is around -0.5 times for the bias of the variance. So the blue one actually is the empirical variance bias times -0.5. We also observed that they will also converge. Unfortunately, by far, we have no idea why. Okay, we did the calculation, we found there's a relation between the bias for the mean and the bias for the variance, but we don't know why. Hopefully, in the future, we can figure out. Now, once we know the bias, so remember what we are trying to do is we are trying to solve this non-Gaussian issue by benchmarking the Gaussian case, right? So in this curve, you can see that there is simulation, Monte Carlo simulation, the square, those are simulation result. And the Gaussian case, which is you assume they're Gaussian, then this the green curve. You can see there's a big gap. So what we can do is by deriving the bias for the mean and the variance, we can correct the result. So if we only modify the mean, we get this purple dotted line. If we only modify the variance, we got the blue dashed line. When we put both the bias for the mean and the variance into the distribution, the result will be very accurate. So basically that means by adding the bias, we will be able to know what is the fundamental limit for a non-Gaussian channel. So that's basically the first work. The following works are similar, but they actually deal with different channel models or basically different mathematical structure for the channel. So the second one is what we call the two-hop large-scale MIMO systems. It can include the relay channel or IRS, RS, intelligent reflecting system channels. So I think some of you should have heard this before. So what is IRS and RS? Although I know industry like Huawei may not be very interested to this because they I don't know, they don't think this is very doable hardware-wise or cost-wise. Anyway, this is theoretical work. So what is IRS? IRS is a planar surface with a lot of antenna elements on it. It was proposed to create an alternative link when the direct link was blocked. So basically, it's more like a reflector. So what we hope we can do is whenever there's no direct link, we transmit a signal, the IRS will reflect it. But the IRS is actually different from a relay because the IRS can only manipulate the phase of the received signal, not the power. Anyway, if you consider the IRS case, we will have a channel model in this way. So there's the first hop from the transmitter to the IRS. There will be the second hop from the IRS to the receiver. And we assume both of them are correlated relay channel. And in between, we have the diagonal phase shift matrix. So that is the new channel matrix we need to deal with when we want to look at the fundamental limits. So to make a remark, actually this phase shift phi here can be adjusted. So you can change it to further improve the performance. Now, we need to still do the two things. We want to know what is the ergodic mutual information. We want to calculate the altitude probability for both of them. We actually need to know what is the statistical behavior of the eigenvalues for the ground matrix constructed by this channel matrix. So the challenge here is this cascaded channel. So there are two random matrices in the channel. We need to make a product and do the evaluation. So I'm not going to go to the detail. Luckily, we could do it. So we basically were able to characterize the mean and the variance for this Gaussian distribution. So basically, we derived the central limit theorem. We proved that this distribution of the mutual information will follow a Gaussian distribution with certain mean and variance. We can determine the mean and the variance, and the parameter can be determined by some fixed point equation. And also the approximation error is determined there. So this is another contribution from a theoretical perspective. Now, this is the result. I'm not going to talk about detail, just observation. The first observation is the approximation is very accurate. As I mentioned before, all the results were derived by asymptotic random matrix series. So we want the n to approach infinite. But if you look at here, the number of antennas we consider is only 4 or 8. And the result is already very accurate. And this observation is not new to us. This was widely observed in the literature by the community. That means even if you derive your result based on asymptotic random matrix theory, still can be very accurate, even for small systems. The second one is whenever you can do the phase shift design, so you change this RS reflection coefficient a little bit, you can improve the performance. Okay, so this is the first one called IRS. But the first one is actually what we call a passive IRS, so it can only change the phase. Now, recently, some people thought about it, say, okay, how about I also change the amplitude? So that means they want to look at some active IRS. So for passive IRS, because you don't change the power, you only change the phase, then the signal, when it goes from the transmitter to the IRS, from the IRS to the receiver, it will experience what we call multiplicative fading. So there are two fading, and this will be very deadly for wireless communication. So whenever you use active IRS, what you want to do is you make the IRS active. So the IRS will not only be able to change the phase, but also change the power to amplify it a little bit. You may say, wow, this is just a relay. Yes, somehow it's similar to a relay, but remember the IRS, the reflecting matrix, is a diagonal matrix. It's not a full matrix as what you can do for conventional relay system. So that's the difference between them. Whenever you consider active IRS, now this will be the signal model. Effective channel is still here. So you have the first hop, you have the second hop, you have the diagonal amplification shift matrix. So it can amplify the signal. But the more important thing is now, besides the noise term at the receiver, you also have a noise term at the IRS, introduced by the IRS. So there are two noise in the received signal. And because of this, the evaluation of the ergodic mutual information becomes difficult. Now you need to take the difference between two ergodic mutual information. The second one was actually created by the noise term. So you need to look at the joint distribution of two mutual information. So the difficulty here is you are looking at the difference and you need to know the joint distribution. So we figure out how to get the joint distribution. And basically, again, it will follow some Gaussian distribution. But here, the difference between this work and the previous one is for this one, we need to know the joint distribution between two mutual information terms, not only one. Okay, so another observation is when the noise in the RS goes to 0, this will degenerate to the previous result, because for the previous one, we don't have noise in the RS position. And secondly, this result can be applied to other two-hop system, including passive, active IRS, and also amplified and forward relay. So this can be utilized for those systems. Here is the simulation result. Again, only the observation. First one, the approximation is very accurate, even when the number of antenna or the reflecting element is not large. Even for L equal to 5, it's quite accurate. Second one, when you increase the size of IRS, you get a better performance. Well, that's intuitive. So for the first two works, for two-hop channels, we consider single mutual information term. The second work is a joint mutual information term. Now let's look at another more difficult one. So physical layer security, I'm not sure many of you guys have heard this before, but actually wireless communication is very vulnerable to eavesdropping because the broadcasting nature, right? So besides using conventional cryptography, those security measures, you can also use physical layer security, which basically exploit the randomness in the noise in the channel to try to limit the amount of information leakage to the eavesdropper. So there are some typical approaches. For example, artificial noise. It means what? It means I know this guy is my user. I know you're trying to listen to our conversation. I'm going to try to send some artificial noise to you, to jam your receiver. That's the first way. The second way is we can do beamforming. I know you are there. I know the eavesdropper is there. I can do beamforming, right? So those are the typical ways to do physical layer security. Now, consider a case where, again, you have IRS because I'm talking about two-hop channel, right? So we set this up in this scenario. So we have IRS, you have a base station. Bob is your deserved user. Sorry, Bob. And Eve is the eavesdropper. And this is the typical name people use. I don't know why, okay? Not Tom and Jerry, it's Bob and Eve. So what happens is, I know Bob is my desired user and there's the eavesdropper. What I'm going to do is I'm going to try to design the transmitted signal, possibly include some artificial noise to reduce the information leakage. Here, we only assume statistical channel information because when people talk about IRS, the biggest challenge people assume is how do you do channel estimation, right? So we only assume statistical channel information here. We don't do channel estimation instantaneously. So for this case, the received signal and Bob and Eve will be represented in this way. So besides the information signal X to Bob, there is also artificial noise. So we add some noise. We send the noise directly to the user and to the eavesdropper. So there are two noise terms, artificial noise and the AWGN at the receiver side. So let's ignore the artificial noise first. If you ignore the artificial noise, there is a performance metric called security rate for physical layer security. So what is the security rate? The security rate is the information rate subtract the information leakage. So basically, you calculate the information rate you can create to the desired user, and you subtract the leakage to the eavesdropper. That is the term, that is the metric we normally want to maximize. Okay, we take the difference into consideration. So you can see here, even without considering the artificial noise, this security rate is already a difference between two mutual information terms. While if we consider the artificial noise, it will be 4. Okay, so it gets more complicated. Compared to the previous work, 1, 2, now we need to deal with 4 because what? Because the artificial noise will also go through the 2 channels. Those will give you 2 other terms. Now you need to calculate the joint distribution of 4 mutual information terms. So for this work, we actually derive a joint distribution for any number of mutual information. We think this is the first work in this area. I'm not sure. We didn't do like exhaustive search of the literature, but we didn't find any result in the related area. Anyway, so this is the last one I want to introduce about 2-hop channel. We have passive IRS, we have active IRS, and this one is for physical layer security. They're all 2-hop channels. Now, the next work I want to introduce a little bit is some preliminary result. It's about holographic MIMO. So as I mentioned before, what is holographic MIMO? So basically, we are trying to reduce the space, the size or the spacing between the 2 antenna elements in the MIMO antenna array. The purpose, 1, I want to find a way to directly manipulate the microwave propagation because this basically, you can imagine this as a space sampling, okay? So in the electromagnetic wave field, you are doing sampling, right? And this will basically increase your sampling frequency. You can make the sample almost continuous. So that's one reason. On the other reason, if you reduce the spacing between the antennas, you can put more antenna, right? You can do a lot of different things. There were some initial results. The good news is we found some work. People have done some work in building up such type of antenna array. They can put more antennas and they can achieve higher spatial resolution. That means your beams will be narrower and the array gain will be larger for this type of MIMO antennas. However, there's also bad news. There are 2 bad news. Maybe starting from the second one, mutual coupling. So whenever you have 2 antennas, you move them together, what will happen is when the first antenna radiates energy out, some of the energy will be leaked to the second antenna. That's called mutual coupling. So when you move the 2 antennas closer, the mutual coupling will be more and more serious. So this is a big issue in terms of antenna design. And secondly, the non-separable correlation structure will disappear. The separable correlation structure will disappear. What do I mean by that? So if we go back to the conventional MIMO channel, we have X here, no matter it's Gaussian or not Gaussian, you have the transmit correlation matrix and the receive correlation matrix on 2 sides of the matrix, right? This is doable because we have a separable correlation. Physically, what does it mean? It means there is no correlation between the transmit antenna and the receive antenna. There's only correlation on 2 sides. So that's why mathematically you can represent it this way. But if you change the antenna, change the design of the antenna, it turns out that at least some experts have shown that this structure will be broken. And what turns out to be a new matrix. This is more complex than this one. Okay, so there are two issues for this channel. There will be antenna coupling, more serious than conventional MIMO system, and also there will be a separable correlation structure. And we need to deal with this channel matrix now. So we have done some preliminary work. So basically, we solved the first one already. The second one still going on. So for the first one, we are able to actually derive the mutual information for non-separable correlation case. So this result is just to show you the effect of the non-separable and the separable. Based on the model we could get by far, it turns out there is a gap when there is different type of correlation. So I want to emphasize that we are system guys, we're not antenna design guys. So all the theoretical work here is based on some model we got from some physical system. So we cannot guarantee this is the general case, but at least we see there's some difference. Okay, let me summarize. So in this talk, I actually introduced three works. The first one is non-center, non-Gaussian channel. Second one, maybe the last one, is holographic channel. So you can see the difference in terms of the channel structure. And the last one is what we call the two-hop channel. Between there's this IRS matrix, which you can use to change the signal. So for the first two works, we actually use the resolvent method. For the last one, we use a Gaussian tools. Both of them are random matrix methods. Why? Because they have their pros and cons, advantage and disadvantage. For example, for resolvent method, the computation is simple. Another advantage is it does not require the distribution of the channel to be Gaussian. So any type of distribution, you can use it. The disadvantage is it is not able to evaluate the approximation error. So I can give you a result, but I don't know how accurate the result is. So that's the problem. And then it's only applicable to column separable structure. That means your matrix should be able to be expressed by separate sum of columns. So there is a little bit of requirement on the matrix structure. Now, compared to resolvent Gaussian method, it can quantify the approximation error. Remember the big O1 over N. That term, that can be calculated by Gaussian tools. It's applicable to most Gaussian random matrix, and the general correlation, no matter what correlation structure you have, we can still use it. The disadvantage is it requires complex computation, only applicable to Gaussian random matrices. Okay. Hopefully this will be helpful if some of you are interested in random matrix theory. In the future, you can use these tools. Okay, conclude. So what we have shown today is using asymptotic random matrix theory, we are able to determine the fundamental limits, the ergodic mutual information, the audit probability for some novel MIMO systems. Also, advantage of using this asymptotic RMT is the solution only depends on some fixed point equation. Once you get that, you get a parameter, you get a closed form expression. The weakness of this type of analysis is it is still a asymptotic result. There is a trade-off between the computational complexity and the accuracy. So for certain cases, the approximation error may be too large. You cannot use it. Okay, here are some future works. As I mentioned before, we are interested in holographic MIMO. But for some of the students here, if you're interested in random matrix theory, I believe machine learning should be the location you apply it. Okay, there are lots of work going on. There are some very interesting, I mean, this is definitely for theoretical machine learning, okay? Not for empirical works. So if you want to know how AI works, this can be a tool to help you. Those are the references I used. Thank you. Thank you very much.
Thank Professor Dong's wonderful talk. So any questions? So it's kind of the idea to combine random matrix theory and
Yep.
communication together.
Yep.
So, and it has potential to be used in machine learning. Any questions?
Yeah.
Hey, Professor Bai.
我看你讲的是 large scale minimal，
对
large scale minimal 跟 massive minimal，
Good question 其实这个也是这个领域的人一直在 argue 的一个点，就是说你说多大叫大，对吧？那 massive 和 x large 其实从数学上没有什么太本质的区别，不是说那里有一个点之后就会发生什么情况，对吧？反正这是我的理解，就是我觉得他们是差不多的。只是从硬件设计的人的角度，可能 scale 会遇到一些问题，但是从我们的角度，我没有看到说有什么 fundamental 的不同。当然，有个问题就是说，当你变大了以后，你的那个信道环境，它们的 correlation structure， 还有你后边能做的各种各样的信号处理，可能都会不一样。比如说信道估计，你可能面对的问题就会大很多，对吧？就这个定量上的问题是存在的。但你说定性上有什么区别？我没有看到什么区别。
现在讲的结果都是表定对话状，都已知性的状态信息
这里所有的工作都是发送端不知道，然后对于两跳的那种情况，我们假设的是 IRS 知道的是统计信道信息，就是他也不知道损失信道信息，只有接收机我们假设知道损失信道信息。对。因为你发送端，如果你知道你可以做 water filling， 你就可以做优化了嘛。我们这里其实都没有做那方面优化。
就是你在那个做那个模型假设，就是 memo 假设的时候，你考虑那个 hybrid 的
你说后边那个，对，其实你是可以考虑的。你如果把 RF chain、number of RF chain 那些东西加进去，你是可以考虑的。但是就等于是那个数学模型前面会再多一块。对，实地中一定对。
它天线虽然增了很大，但 RF chain 有限，
数量有限，
前面还是一个相同阵。
对，在那块是数学上是可以加进去的，只是我们现阶段主要是想从0到1嘛，就是先把这个问题解了，将来如果有可能再把那个加进去。对，那个绝对是，尤其是 massive memo 一定面对这个很大的问题，对吧？
我有一个问题，就是您的工作都是根据，就是你举的几个例子都是根据它的一些抽象的数学模型来得到，就是它的相当于那个MI 跟那个中断概率的方法。然后会不会说我这个模型已经是抽象到了一定程度了，然后如果我需要加入一些更具体的约束之后，然后我的后面所得到的结论就完全就不一样，或者颠覆掉了。
这个有可能，我同意你的说法，就是这个领域的工作其实它有点 idealistic， 它一定会把这个模型简化到一定程度，否则我们就是 not tractable 嘛。就比如说像 Bob 刚才说的，如果我把那个 hybrid 这个 precoding 加进去，那前面这些模型都不成立的。你能得到那些 gain， 其实会，如果你的 RF chain 降低下来，你的那个数据流肯定就 significantly drop， 对吧？这个只是在理论上假设我们硬件上没有任何问题的前提下做到的，但实际系统里现在很多具体的问题就是说硬件你都根本做不准，对吧？你连同步可能都有问题，那这个只是一个 bug。这个也是为什么这个东西叫 fundamental limits 嘛，就是从理论上它是一个上界，但实际上系统跟上界那个距离还很远很远。但是我们知道的是，就是你把天线做多了，反正它肯定会好，只是说大家还是离那么远嘛，但是大家都变好了，这只是说，所以你说那是对，如果有很多限制，那个性能会差很多。对 ，OK，Thank you，Thank you, Professor Song.
Thanks, Professor Song again for the wonderful talk. Now let's invite our last speaker today, Professor